मैं स्टार्ट ही आएंगे.
Okay, yeah, thank you. Okay, good morning all. So we are having a 1 week long lecture series, online lecture series on different aspects of ocean modeling. Essentially, the idea of this course is to introduce participants on basic elements of ocean modeling. So we may not be going into the details of ocean modeling because it's a very short-term course, and we will be covering ocean circulation modeling. Then within that we will be going a little more detail on the modeling of tides and their applications. Then biogeochemistry, we will talk on wave modeling, storm surge modeling, tsunami modeling, and then we will have a kind of demo because in this online platform it may not be easy for us to arrange practical sessions. So we will give
couple of
you a
minutes
demo
for people
on
to rejoin.
operational system.
There was a break in the live streaming,
So
and
that is what we
installed
plan
it,
as part of this
people have to refresh
lecture
their
series. So today's
browser
lecture
or
is
YouTube.
basically
So
on the ocean
just
gas
wait for a
circulation
couple
modeling.
of minutes.
Myself, Francis,
may not take more than
I work as
10-15
an ocean
minutes to
modeler
complete
in COIS. We configure ocean modeling systems for the operational purposes, operational ocean forecasting systems. Let us quickly look at what is an ocean model. Basically, today's lecture it will be what will be ocean circulation modeling, and what are the different components of this system and how we configure them. So it's a very much like a bird's eye view of ocean modeling. And for any detailed information, you can directly reach to me. So ocean model, circulation model in ocean is essentially a climate model. So there is no big difference between the climate models or ocean models what we use. So essentially they represent the large-scale ocean atmospheric processes, and that we know that they are very important for the understanding the climate variability or climate change in different space and time scales. Also, we know that these are important tools for not only for climate studies, but they are very important tools for predicting the ocean. See, whether it's a very short-term prediction or long-term projections like climate projections, we depend on ocean models. There are a couple models. There are standalone models. What we talk today is mostly on a standalone ocean circulation model. We know that the ocean and atmosphere is in constant touch. They interact in all time and spatial scales. So it is not that easy for us to represent all these scales of interaction into the ocean models because of inherent limitations of the modeling. So first important part of any modeling is to identify the most critical processes that we need to model. So that is the
welcome back. So we were talking about the vertical coordinate system.
When you start doing an ocean
coordinate
model
system,
we should
and
be
now
very clear that
we were talking
this
about
is
the
the
sigma
process that
coordinate
I'm
system, where
interested to look at.
the
This
coordinate,
is the
vertical
process
coordinate
that
is
I'm
essentially a
interested to
terrain following
project or
coordinate
forecast.
system. So
then what are
at any given point of
represented in the model?
location,
what kind of model we should
we
use?
will not
what
have a
should
discontinuity
be
in the
boundary conditions we should apply
vertical
to get
layers.
such processes.
All layers
right?
will be
So that is the
included
critical part of ocean
the
model,
location is.
apart from the technical
Only
part of
difference
nature.
is that if you have a shallow
So let us
bathymetry,
first try to
then
define
all the levels will be
what is an
squeezed
ocean
to
model.
this
Any general circulation model for that matter.
depth. Whereas
It's a
if
mathematical
the depth is much
representation
deeper,
of processes.
then it will be stretched.
Quite often they are represented in
There are
particle
parameters
layers,
which
such
you
processes.
can
Processes can be physical processes.
to get the desired
vertical biological location. Apart from
depth in the vertical
only difference is that
layers.
if you have a shallow
thickness
so
of the vertical
let us
layers,
first try to
if you want
model
long layers in
what
the
is an
surface,
ocean that happens over
tune
the
that.
any
If you
general
want long layers in
has
the
its own depth. In whereas a mathematical representation of processes, it will be stretched. Quite often they are represented in
There are
particle
parameters
layers,
which
such
you can
processes.
processes
Can
can
be
with
physical
the
processes. We have to specify biological location. Apart from
depth in the vertical
different layers.
can you refresh
So let us try to model
just a
what is
I
an
will
ocean that happens
talk to
over
the
any
technical
general
layers in
has
the
its own depth. In whereas mathematical representation of processes, it will be stretched. Quite often they are represented in particle layers, such processes can be physical processes. We have to specify biological location. Apart from depth in the vertical different layers. Can you refresh? So let us try to model what is an ocean that happens to any general layers has its own depth. In whereas mathematical representation of processes, it will be stretched. Quite often they are represented in particle layers, such processes can be physical processes. We have to specify biological location. Apart from depth in the vertical different layers. Can you refresh? So let us try to model what is an ocean that happens to any general layers has its own depth. In whereas mathematical representation of processes, it will be stretched. Quite often they are represented in particle layers, such processes can be physical processes. We have to specify biological location. Apart from depth in the vertical different layers. Can you refresh? So let us try to model what is an ocean that happens to any general layers has its own depth. In whereas mathematical representation of processes, it will be stretched. Quite often they are represented in particle layers, such
I'm sorry about that. Let us check whether it is okay now. So what we were talking about was the sigma coordinate system, and then there is one more coordinate system which people use, particularly if there is specific studies, process studies. Then this is called the isopycnal coordinate system. In this coordinate system, people use potential density to a given reference pressure level as the vertical coordinate. So essentially what the distribution of the layers will be based on the potential density distribution. So the advantage is that, okay, it's good if you are talking about transport of traces, because we know that it happens along the same density gradients. But if we are interested in specific processes which has a cross isopignal mixing, then this coordinate system is not useful. Particularly in the coastal application, this may fail. So we have come across three systems, and now and they have advantages and disadvantages. The current trend is that, okay, people make use of the good points of different coordinate system and come up with a hybrid coordinate system. HICOM was the first one to do that hybrid coordinate system, and now the recent version of MOM 6 also make use of this hybrid coordinate system. This is the new era of vertical coordinate system in the ocean models. Also, in the horizontal discretization, there are two different classes of discretization. One is structured grid and another is unstructured grid. Structured grid means you have basically it's a Cartesian kind of a coordinate system, and the coordinates are orthogonal. It can be curvilinear or it can be kind of uniformly distributed, but essentially they are structured grids. And the structured grid, the advantage is that, and mostly they use the finite difference key to resolve the numerical expressions. So the models like MOM, POM, or HICOM, ROMS, all these uses structured coordinate system. Whereas the models like FBCOM or ADCIRC, they make use of the unstructured grid. So the advantage of unstructured grid, you can see in the picture. Suppose you use a structured grid, then there are certain places near the coast, the grid is empty, or the ocean is not well represented within a grid. Whereas if you have an unstructured grid, you can use this for complex coastline structures. So this is the advantage, and FBCOM is one of such model which is in a general circulation framework. That means it has all the 3D dimensions, and these are very good for coastal applications and applications for estuaries and regions with complex coastlines. Now, we will summarize the steps involved in the ocean circulation. So, first thing is that definitely we have to define the problem, what purpose the model is configured, the processes which are important, and identify the most suitable domain for the model. That is important, whether you want a global model, you want a regional model. This information has to be kept ready, and that will be the important factor that determines the domain of the model. And identify the most suitable coordinate system. So you want what kind of vertical coordinate system you are looking at. If you are simply using it for a coastal application, then probably a sigma coordinate system is the best. Whereas if you are looking for a climate scale application, maybe Z coordinate system is sufficient. And then identify the most suitable model. Certain models are tuned or designed for certain applications. For example, if you want to model a wave, then there is no point in using a model called ROMS or POM. You have to use models like WaveWatch or SWAN or that kind of a model. Or if you are interested to look at the tsunami or storm surge or paratropic kind of propagations, then probably an ADCIRC model is the best solution for that. On the other hand, if you are looking at a circulation feature, general circulation, temperature distribution, the vertical as well as the horizontal, then you may have to go for a 3D circulation model. That too, you have to choose which model has which coordinate system. Suppose you are interested to use the hybrid coordinate system, then there are only a couple of models which you can choose. So identify the most suitable model for you, and then, as I mentioned in the previous slides, you have to identify the best resolution for your model setup depending on the physics you are considering, the region you are interested. So identify the best resolution for the model. And then the atmospheric forcing, boundary forcing is important. Also, if you are using some other forcing for the tracer initialization and all, okay, you need to identify the best forcing parameters. Then mixing parameterizations, or the representation of the vertical distribution of short wave radiation. So these parameterization schemes are different in different models. Maybe a model has different options. You have to choose the right scheme for that, tune that model, that parameterization for your application based on the certain observations you have in your hand, and then identify the initial and boundary condition to start with, because ultimately you are solving a partial differential equation. So you need to give the initial and boundary values to integrate. Once you have a clear understanding on the model which you are looking at and the domain and all, okay, now go back and then download the model which you have chosen, and then port it to the computer you are interested in. Then the steps involved are, okay, you need to prepare a grid for the model. That means that is the structure of your model. What kind of vertical grid, what kind of horizontal grid, all those information will go into the grid preparation level. Then decide how many levels you require. Again, as I said, what kind of resolution you require. This has to be decided based on the requirement. And then prepare your initial and boundary condition. Many models may require you to, put the initial or boundary condition into the format, a specific format that can be read by the model. So this is part of the pre-processing solution. Then same thing, forcing also you may have to prepare. Once you have chosen, then you prepare in the required format, boundary conditions and initial conditions and forcing. And define the empirical constant and coefficient based on the requirement, and choose the appropriate time stepping, what you are interested, because if you are particular about kind of solving a very fast waves, then probably you may have to choose a very high frequency time stepping. Similarly, if you have a very high resolution model, then you have to have very small time stamps for the solving the equation without blowing it up. So choose that, and then you are ready, your model started running. Then what frequency you require the output, you have to choose that, and what are the parameters you require in the output. Those things you have to provide into the specific files or the input regions where you have to give. Then integrate the model, you get the output. Okay, so now that's all about the ocean modeling, and then I will quickly summarize the kind of ocean modeling framework we have right now for the operational forecasting system. INCOIS is an operational agency, so the modeling what we do here ultimately translates to an operational forecasting system. So we have a very robust forecasting system here. We call it as HOOFS, high resolution operational for ocean forecast and reanalysis system. This is for the Indian Ocean, and it uses boundary conditions from global ocean data assimilation system, the lateral boundaries, and also it uses atmospheric forcing from National Center for Medium Range Weather Forecast and CMRWF. The atmospheric parameters required to force these models are taken from that. And we have two sets of models. One is for the Indian Ocean and another is for the northern part of the Indian Ocean. The Indian Ocean model, you can see in the right hand side, it is covering a space, spatial coverage is 30 degrees south to 30 degree north and 30 degree east to 120 degree east. So this is the special domain. This has a special resolution about 1 by 12 degree resolution. And when we come to the northern Indian Ocean, where we have much more information required, much more higher resolution is required, the resolution of the model is 1 by 48. It covers part of Arabian Sea and most of the Bay of Bengal. Very high resolution, and these models exchange boundary condition. So the Indian Ocean model gives boundary condition for the Northern Indian Ocean model, and in turn the Indian Ocean model takes boundary condition from the global model, which is the global ocean data assimilation system. And the observations are going into the model as part of the data assimilation system. This entire system is called regional analysis for the Indian Ocean. So this is a ocean model plus a data assimilation system. Again, the model used is the Indian Ocean model, the same regional ocean modeling system, and the data assimilation based on localized local ensemble Kalman filter LETKF is used to give the data simulations into the ocean model, and this is how we set up our ocean forecasting system. The system provides different parameters. We get physical and biogeochemical parameters from this model, and that they are used for different purposes for the Indian Ocean domain. So I just give, this is just to give a brief of what forecasting system we have. You can get a detailed view of this system from this paper France et al. 2020. This is already published. Okay, so now let us summarize what we learned today. We got a general overview of climate models, governing equations, and important features of the ocean circulation, ocean mixing processes, and how we represent this mixing process in the ocean models. What are the different vertical and horizontal coordinate systems used in ocean models, and basic steps involved in configuring a physical model. That's the practical steps involved. And then I just summarized what is the high resolution operational ocean forecasting system. So I'll stop here. Let me see if I can see the questions in the chat box. Because of the switchover in different YouTube links, I'm not very sure I'll be able to find all the questions, but whatever I find, I will try to answer. Thank you. Sorry, for some reason I am not able to see any chat in my chat box, probably because of these issues. So those who have queries, please feel free to write to me. My email ID is given here, francis@incois.gov.in. I will be happy to respond to them. I'm sorry about that. Thank you all. Have a nice day.